The galaxies you see at night are all connected by a hidden superstructure. This is the great cosmic web, the true skeleton of our universe. For centuries, we mapped isolated stars, completely missing the dark filaments and colossal walls that tie everything together. By the end of this journey, you will see the universe not as a collection of random lights, but as a single, intricate organism. How did this vast architecture first emerge from nothing, and what force is now secretly tearing it apart? What does it feel like to finally discover the map of all existence? The deepest truth about the cosmic web is written in the emptiness. Look at any detailed map of the universe, and your eye is drawn not to the bright knots of galaxies, but to the colossal black patches in between. These are the cosmic voids, unimaginably vast regions that appear to contain almost nothing at all. But this emptiness is an illusion. A void is not a true vacuum. It is a cosmic desert, a region where matter is so thinly spread that it might hold only a handful of galaxies, where a supercluster would contain millions. This profound scarcity creates the perfect environment for the universe's most mysterious force to dominate. Within these empty tracts, dark energy meets the least resistance, stretching the fabric of space itself and accelerating the expansion of the cosmos. For a long time, astronomers saw these voids as mere blanks on the map, uninteresting absences. Then came the pivotal realization: the voids were not random. Their shapes, their sizes, their very existence followed a pattern. They were the negative space in a cosmic painting, and by carefully studying their outlines, scientists could begin to infer the shape of the positive structures they surrounded. It is like mapping a mountain range by meticulously charting its valleys. You come to understand the peak by understanding the absence that defines it. This was the revolutionary shift in thinking. The grand architecture of the universe, the cosmic web itself, was built as much by absence as by presence. The voids were the crucial evidence that the distribution of matter was structured, that there had to be dense walls and filaments boxing in these immense emptinesses. To truly see the skeleton of reality, we had to first learn to see the shape of the nothingness. And it is this very contrast, the stark difference between the barren voids and the brilliant nodes, that finally makes the entire cosmic web visible to us. The most brilliant cities in the cosmos are not made of steel and light, but of galaxies themselves. At the densest intersections of the cosmic web, gravity has woven thousands of galaxies into a single, colossal structure known as a galaxy cluster. Think of our own local group of galaxies, with Andromeda and the Milky Way as a quiet neighborhood. A galaxy cluster is a sprawling metropolis, a gravitational anchor point where the universe's fundamental forces are on full display. The Perseus cluster is one such metropolis, a realm where thousands of galaxies swim in a sea of superheated gas, a plasma so immense it glows with the energy of X-rays. This glowing halo is a direct testament to the incredible gravitational well these galaxies collectively create, a pit so deep it traps matter and bends the very fabric of space around it. Within these clusters, the ghostly hand of dark matter is felt most powerfully. The sheer amount of gravity required to hold these rapidly moving galaxies together far exceeds what the visible matter can provide, offering some of the strongest evidence that an invisible scaffold is holding the entire city in place. This immense gravity also acts as a natural telescope. It warps the space around it, bending and magnifying the light from galaxies that lie far behind it in a process called gravitational lensing. This allows us to peer even deeper into the cosmic past, using these clusters as magnifying glasses to see what would otherwise be invisible. These luminous nodes are not isolated islands. They are the grand central stations of the cosmic web, the endpoints where the universe's great filaments converge. By studying their precise positions and properties, we can begin to trace the invisible lines of force that must connect them, mapping the luminous hubs to uncover the dark architecture that binds them all together. These vast cosmic highways are the final piece of the map. Stretching between the brilliant galaxy clusters and the immense walls are the filaments themselves, thread-like structures of dark matter and diffuse gas that form the true backbone of the cosmos. Galaxies are strung along these tendrils like luminous pearls on an invisible string, tracing out paths that can stretch for hundreds of millions of light years. The Sloan Digital Sky Survey gave us our first three-dimensional view of this intricate network, revealing a universe not of random scatter, but of deliberate, elegant connection. It showed us a cosmos crisscrossed with these ghostly bridges, a web of light and matter on the grandest possible scale. Within these filaments, the universe conducts its business at a gentle, patient pace. Diffuse gas, drawn in by gravity, slowly cools and condenses, flowing along these cosmic rivers over billions of years to feed the growing galaxies at their ends. This is where the balance of the universe is most evident, a delicate dance between the relentless inward pull of gravity and the outward push of cosmic expansion. Mapping this intricate system is like tracing the root network of a colossal tree, following the hidden channels that deliver nourishment to the brightest flowers, the galaxies themselves. To truly see this ghostly architecture, however, we had to learn to look at the sky in an entirely new way. We needed a method that could reveal the structure of the unseen. For centuries, our maps of the cosmos were flat. We could chart where a galaxy sat on the two-dimensional dome of the sky, but we had no way of knowing its true location in the vast depths of space. The key that unlocked this third dimension was a simple color change in the light of distant galaxies, a shift toward the red end of the spectrum. This redshift is the universe's fingerprint of expansion. As space itself stretches on its immense journey from a distant galaxy to our telescopes, it stretches the light waves within it, lengthening them and making them appear redder. The greater the redshift, the farther away the galaxy, and the farther back in time we are looking. This single measurement transformed astronomy from a cartographer's sketch into a sculptor's model. Pioneering surveys in the 1980s, like the one from the Harvard-Smithsonian Center for Astrophysics, began the monumental task of collecting these redshifts for thousands of galaxies. For the first time, we could place galaxies not just by their right ascension and declination, but by their true distance from us. And as those points were plotted in three-dimensional space, a pattern began to emerge from what had seemed like cosmic noise. The galaxies were not scattered like random dust. They were concentrated into great walls and sweeping filaments, with those immense, haunting voids stretching between them. This was the moment of revelation. The cosmic web was no longer a beautiful theory. It was an observed, measurable fact. Each subsequent survey built upon this foundation, adding millions of data points to our cosmic census. Projects like the 2-degree field galaxy redshift survey and the Sloan Digital Sky Survey meticulously filled in the map, revealing a structure of breathtaking complexity and interconnectedness. This was a data-driven revolution, a slow and patient unveiling that showed us the universe possesses a coherent architecture. This grand design, this blueprint for all existence, points directly back to the universe's very first moments. The entire intricate pattern of the cosmic web was imprinted in the fabric of reality from a single primordial seed. every single galaxy and cosmic void traces its origin back to a ghostly whisper from the beginning of time. In the first fleeting fraction of a second, the universe underwent a growth spurt of unimaginable speed, a period cosmologists call inflation. Space itself expanded faster than the speed of light, stretching a subatomic volume to something larger than our entire observable cosmos in a blink. And within that furious expansion, the fate of the cosmic web was sealed. The vacuum of space at these energies was not perfectly smooth. It was a quantum foam fizzing with tiny, temporary fluctuations. Particles and energy would pop into and out of existence, creating microscopic ripples in the fabric of reality. Inflation acted like a cosmic amplifier, stretching these quantum ripples to astronomical proportions, freezing them into the very geometry of the universe. Those faint ripples were the primordial seeds of everything. A region with a tiny bit more density had a tiny bit more gravity. Over billions of years, that extra gravity acted like a magnet, slowly pulling in surrounding dark matter and gas. The slightly denser patches grew into the first stars, then galaxies, then the great clusters and filaments. The slightly emptier patches evolved into the vast cosmic voids. The entire intricate architecture of the cosmic web, with all its splendor and scale, is the grown-up version of those infant quantum whispers. This incredible story leaves a tangible piece of evidence, a cosmic fossil we can observe today. The pattern of those initial fluctuations is permanently imprinted on the oldest light in the universe, the cosmic microwave background radiation. This afterglow from the hot, dense infancy of the cosmos carries a specific pattern of hot and cold spots, a map of the density variations that would one day become the great walls and empty void. It is a direct link between the quantum realm and the cosmic scale, a stunning confirmation that the largest structures we see were born from the smallest possible events. That ancient snapshot of the infant cosmos holds a secret code within its nearly uniform glow. The cosmic microwave background is the oldest light we can see, a fossilized remnant from a time when the universe was a mere 380,000 years old. Before this moment, the cosmos was a searing, opaque fog of plasma and light. As it finally expanded and cooled enough for atoms to form, light was set free, embarking on a journey across the ages that ends in our telescopes today. This light does not show a perfectly smooth canvas. The most detailed maps, like those from the Planck satellite, reveal it is subtly mottled with tiny temperature variations, a patchwork of hot and cold spots. These differences are incredibly slight, variations of just 1 part in 100,000. Yet these minute ripples are everything. Each slightly warmer patch marks a region where the primordial universe was a tiny bit denser, a gravitational seed that would, over billions of years, attract dark matter and gas. Each cooler spot signifies a region that was slightly more empty, a potential future void. The entire blueprint for the cosmic web, with its great clusters and filaments, is written there in that faint, ancient pattern. By meticulously analyzing the statistics of these spots, cosmologists can run the cosmic film backward. They can test theories of the universe's explosive birth, of inflation, and predict with stunning accuracy the statistical distribution of galaxies and voids we should see in our modern universe. The cosmic microwave background is the ultimate Rosetta Stone, allowing us to translate the conditions of the first instant into the sprawling galactic cities we observe today. It confirms that the potential for this immense structure was imprinted at the very beginning. But this luminous map only shows us half the story. To truly see the web in its entirety, we must learn to perceive the invisible scaffolding that gives this blueprint its form and strength. The blueprint was set, but the universe needed a builder. That builder is dark matter, an unseen substance that sculpts the cosmos through gravity alone. It emits no light, absorbs no light, and passes through ordinary matter as if it were not even there. We cannot see it, but we can feel its gravitational hand everywhere. The way galaxies spin far too quickly for the gravity of their visible stars to hold them together, the way massive clusters of galaxies bend the light from more distant objects, acting as natural telescopes. These are the ghostly fingerprints of the invisible architect. Dark matter's gravity was the primary force that took the faint seeds from the cosmic microwave background and amplified them. Because it does not interact with light or repel itself through electromagnetic forces, dark matter was free to collapse under its own gravity first. It formed a vast, invisible skeleton long before the first stars ever ignited. This dark scaffold created deep gravitational wells, a cosmic landscape of hills and valleys. Only then did ordinary matter, the gas and dust we can see, feel this pull and begin to flow. It cascaded down into those pre-existing dark matter valleys, pooling to form the galaxies and the glittering filaments we observe. This sequence is crucial. The dark structure had to form first to provide the template for everything else. The proof lies in our computers. When scientists simulate the evolution of the universe and include the gravitational effects of dark matter, the result is a cosmic web that looks exactly like the one we see through our telescopes. It produces the great walls, the filamentary bridges, and the vast voids with stunning accuracy. Remove dark matter from the simulation, and the beautiful, intricate structure simply fails to form. The universe remains a formless, scattered haze. Dark matter is not a minor component. It makes up about 85% of all the matter in the universe. This means that everything we can see, every star, every planet, every nebula, is just the visible tracing, the luminous decoration, on a framework made of something we cannot see. To understand why the cosmos looks the way it does is to understand the nature of this mysterious substance. So how do we possibly map an invisible skeleton? We must learn to watch how it makes the universe itself bend. The invisible architecture of the cosmos reveals itself through subtle distortions. To map the dark matter filaments, astronomers use a phenomenon called weak gravitational lensing. Imagine the fabric of spacetime as a perfectly clear sheet of glass. Now place a heavy, invisible object on it, like a dense knot of dark matter. The glass warps. When the light from a galaxy billions of light years behind this warp travels toward us, its path bends, and its image is subtly stretched and sheared. It is not a dramatic funhouse mirror effect, but a tiny, almost imperceptible distortion. A single galaxy's shape tells us very little, but by analyzing the shapes of millions of distant galaxies, a pattern emerges. If vast numbers of these background galaxies appear slightly stretched in a common direction, it points to an invisible mass in the foreground, bending their light like a colossal lens. This is how we trace the unseen. Massive collaborative projects like the Dark Energy Survey have undertaken this monumental task, using powerful telescopes to photograph huge swaths of the sky and measure the shapes of countless galaxies. Their work produces breathtaking three-dimensional maps of mass, not light. These maps reveal the ghostly halos of dark matter enveloping galaxy clusters, and more importantly, the faint, wispy tendrils of the cosmic web stretching between them, exactly as the simulations predicted. We are no longer just inferring the dark skeleton, we are charting it directly by watching it twist the light of the universe. This confirms a profound truth. The glowing galaxies we see are merely the brightest ornaments on a framework built from something we cannot see. And while this dark framework dictates the structure of the cosmic web, another, even more dominant force is controlling the ultimate fate of the entire stage. This silent, relentless pressure is reshaping the entire cosmic stage. As we meticulously chart the web's grand architecture, we must also confront the mysterious force that is actively stretching it thin, a phenomenon known as dark energy. Imagine dark energy as a fundamental property of empty space itself, a kind of anti-gravity that pushes the universe apart. For billions of years, the attractive force of dark matter's gravity was the dominant player, tirelessly pulling matter together to build the great clusters and filaments. But as the universe continued to expand, matter became more and more spread out, its gravitational influence weakening. In this growing void, dark energy found its moment. Around 5 billion years ago, it began to dominate the cosmic balance. Think of it as a cosmic tug-of-war. On one end of the rope, dark matter pulls inward, trying to build structure. On the other end, dark energy pushes outward, accelerating the expansion of space itself. This repulsive force now acts as a brake on the growth of the cosmic web. It makes it harder for new, vast filaments to form and for existing structures to pull in fresh material from the intergalactic deserts. The web is still there, but its future growth is being systematically stifled. We measure this influence by comparing the universe's large-scale structure at different epochs. By looking at distant, ancient galaxies, we see a time when the web was still actively collapsing and growing. When we compare that to the more modern, nearby universe, we can detect the subtle signature of dark energy slowing that growth down. This leads to a profound and startling prediction for the far future. If dark energy continues to dominate, its influence will only strengthen as space expands. Billions of years from now, it may begin to tear the cosmic web apart. The delicate filamentary bridges that connect galaxy clusters could be stretched and severed. Galaxies on the outskirts of clusters would find their gravitational ties cut, left to drift alone into the expanding darkness. New superclusters would never have a chance to form. The universe would become a collection of isolated galactic islands, growing ever more distant from one another in an ever-cooling sea of emptiness. To truly witness this grand cosmic story, from its explosive birth to its uncertain future, we need to look back in time. Our own telescopes are time machines, and the light traveling across the void carries with it the entire history of the cosmic web's evolution. Our telescopes are time machines, and by pointing them at different cosmic distances, we can watch the universe grow up. Each redshift measurement is a timestamp, placing a galaxy at a specific chapter in the life story of the cosmos. When we assemble these snapshots in order, a grand cosmic movie begins to play, revealing the slow, majestic evolution of the great web. The early scenes show a universe that looks fundamentally different from our own. Billions of years ago, the cosmic web was a faint, ghostly sketch. The filaments were tenuous bridges of gas and dark matter, and the galaxies they connected were small, fragile things, mere proto-galaxies still in the process of formation. There were no brilliant, sprawling galaxy clusters yet, no clearly defined walls. It was a more chaotic and diffuse cosmos, a universe of potential waiting for gravity to do its work. This youthful state is captured in incredibly deep observations like the Hubble Ultra-Deep Field. In that tiny, dark patch of sky, we see thousands of these infant galaxies, a crowd of faint, bluish smudges. They are not neatly arranged, they appear more randomly scattered, a bustling, primordial crowd before the cosmic architecture had fully hardened. This is the web in its infancy. Then the great sculpting begins. Over billions of years, gravity acts as a relentless, patient artist. It pulls matter along the invisible filaments of dark matter, guiding streams of gas and young galaxies toward the intersections of the web. The nodes begin to fatten, growing from small groups into the magnificent galaxy clusters we see today. As matter flows into these dense hubs, the voids between them become ever more empty, their boundaries sharpening. The universe transforms from a formless cloud into a structured, hierarchical network. We can witness this transformation directly by comparing the ancient universe seen by Hubble with the detailed, local maps from surveys like the Sloan Digital Sky Survey. The difference is staggering. One shows a chaotic nursery, the other a mature, interconnected metropolis. This historical record is not just a fascinating story, it is a rigorous test for our entire understanding of cosmology. The fact that our simulations, based on the laws of physics and the initial conditions seen in the cosmic microwave background, can accurately reproduce this entire multi-billion-year progression is a triumph of modern science. It confirms the grand timeline from a smooth, hot beginning to the complex cosmic web we inhabit. To read the next chapters of this story with even greater clarity, we must learn to listen to the universe in a different language, one written not in light, but in the violent collisions of the cosmos itself. The cosmic web glows with a light our eyes can never see. A significant portion of the ordinary matter in the universe is not locked up in stars or planets, but exists as a superheated, thin gas that fills the immense spaces within galaxy clusters and along the vast filaments. This intracluster medium is heated to temperatures of millions of degrees, a state so energetic that it does not shine in visible light, but instead emits a fierce, penetrating glow in the X-ray part of the spectrum. For decades, this component of the cosmic web remained completely hidden from our view. It was a ghost of normal matter, theorized but not seen. Then, space observatories like Chandra and XMM Newton turned their sensitive instruments toward the heart of massive galaxy clusters. The images they sent back were breathtaking. They revealed colossal, shimmering clouds of this multimillion-degree gas, halos so massive that they often contain more ordinary matter than all the stars in all the cluster's galaxies combined. This was the moment we realized the most massive visible part of a galaxy cluster is not the glittering cities of stars, but the invisible, scorching ocean in which they float. More recently, astronomers have achieved an even more difficult feat. They have managed to detect the faint X-ray whisper from the warm hot gas that suffuses the cosmic filaments themselves. This is a landmark discovery. For years, a portion of the universe's normal matter, the so-called missing baryons, was unaccounted for. We knew it had to be there, but we could not find it. This faint X-ray glow from the filaments confirms that a vast reservoir of ordinary matter has been hiding all along in these diffuse intergalactic rivers, heated by the violent journey of falling into the web's gravitational embrace. This hot gas is a fossil record of the cosmic web's violent construction. As matter was funneled at high speed along the filaments and into the dense clusters, it created colossal shock waves, similar to a sonic boom but on a cosmic scale. These shocks heated the gas to its incredible temperatures, leaving it as a permanent thermal imprint of the universe's structure formation process. By studying this X-ray emission, we take a census of the universe's normal matter and understand the powerful forces that govern how galaxies form and evolve. This hot, energetic component adds a crucial new dimension to our map. We no longer see the cosmic web as a simple skeleton of dark matter and galaxies. We see it as a dynamic thermal system, a universe pulsing with heat and violent history. To grasp the full picture of this cosmic ecosystem, we must learn to listen to the universe in an entirely different way. The faintest signals in the cosmos often tell the most profound stories. While X-rays reveal the universe's scorching heat, a quieter, colder reality is broadcast on a different frequency. Radio astronomy listens to the whisper of neutral hydrogen, the most fundamental building block of the universe. This simple gas, a single proton paired with an electron, fills the vast intergalactic spaces, threading through the dark matter filaments of the cosmic web. It is the primary fuel for star formation, the raw, unlit material from which all galaxies are born. For decades, this reservoir of potential was largely invisible to us, its story silent. But hydrogen has one telltale signature. When the spin of that lone electron flips, it releases an incredibly faint radio wave at a specific wavelength, 21 centimeters long. This whisper is so weak that it can travel across billions of light years without being absorbed or scattered, carrying a pristine message from the darkest, most diffuse regions of space. Catching this signal requires a new kind of ear, an instrument of almost unimaginable sensitivity. Projects like the Square Kilometer Array are not single telescopes, but vast fields of radio antennas spread across continents, working in concert to form a single, colossal ear tuned to the universe. This emerging network is designed to do something revolutionary, to map the distribution of neutral hydrogen across unprecedented cosmic volumes. This will allow us to trace the cosmic web in a way that is completely independent of starlight. We will no longer be mapping just where the galaxies have already ignited, but where the potential for new galaxies still resides. We will see the faint, gaseous tendrils that are too diffused to glow in any other light, tracing the rivers of cold fuel that flow along the cosmic skeleton. This is the key to understanding how the web functions as a living system. Galaxies are not isolated engines of star formation. They are constantly fed by this intergalactic rainfall. Hydrogen gas, guided by the invisible pull of dark matter, streams along the filaments and slowly pools at the nodes, providing the steady nourishment required to build new generations of stars. By listening to the 21-centimeter whisper, we are essentially hearing the story of cosmic nourishment, the process that turns raw potential into brilliant reality. This radio view, combined with the insights from optical and X-ray astronomy, is giving us a multi-sensory map of the universe. We are no longer just seeing the cosmic web. We are beginning to feel its texture and hear its history, building a complete picture of the dynamic structure that defines our existence. The most brilliant beacons in the cosmos shine from its farthest shores. Quasars are the active hearts of ancient galaxies, powered by supermassive black holes feeding on unimaginable amounts of gas. Their light is so ferociously intense it can outshine an entire galaxy, traveling for billions of years before reaching our telescopes. This journey makes them more than just distant curiosities. It transforms them into perfect cosmic flashlights. As a quasar's light races across the universe, it does not travel through empty space. It passes through the tenuous gas that clings to the cosmic web, the very filaments and protovoids that existed when the universe was in its youth. And this gas leaves a ghostly fingerprint on the light, a signature of its presence. Specifically, clouds of neutral hydrogen absorb a very particular wavelength of light, a signature known as the Lyman alpha line. When astronomers finally break the quasar's light into a full spectrum, they see something astonishing. Instead of a single, clean absorption line, they find a forest. The spectrum is notched with thousands of tiny, dark lines, each one a separate cloud of hydrogen that the light has passed through on its long journey. This is the Lyman alpha forest, a direct record of the cosmic web's raw material. By reading this forest, scientists can perform a kind of cosmic tomography. Each absorption line tells them the density of a hydrogen cloud and its redshift, which reveals its distance. The line of sight to a single quasar becomes a one-dimensional core sample, a thin straw punched through the universe that records every ripple and cloud of gas along its path. It is like hearing the echo of a single voice in a vast canyon and being able to map every stone and crevice the sound wave touched. But one core sample is not a map. The true power emerges when we combine the data from thousands of quasars, each one probing a different line of sight. Statistically, the patterns begin to overlap and intertwine. Where the absorption forests from different quasars show similar structures at similar distances, we can begin to infer the shape of a vast, interconnected network. We can statistically reconstruct the three-dimensional distribution of this primordial hydrogen, tracing the faint, wispy filaments that existed before gravity had fully sculpted them into the brilliant galaxies we see today. This method reveals the cosmic web at its most fundamental, showing the distribution of its most basic building block. It allows us to see the universe not as a collection of finished cities, but as a blueprint of flowing rivers and empty basins, a snapshot of potential caught in the act of becoming structure. The data from these ancient flashlights is now being woven together with maps from weak lensing and galaxy surveys, merging the past and present into the most complete picture of the cosmic web we have ever seen. These modern cartographers are charting the cosmos on a scale once thought impossible. The Dark Energy Spectroscopic Instrument, or DESI, sits atop a mountain in Arizona, its robotic eye capable of precisely targeting 5,000 galaxies at a single time. Every night, it collects the light from these distant islands, breaking it into spectra to measure their redshift and thus their distance. Its mission is to create a three-dimensional map encompassing tens of millions of galaxies, a chart so vast it will trace the subtle gravitational hills and valleys of the cosmic web across a third of the visible sky. This is not a static snapshot. It is a dynamic census of the universe's large-scale structure, allowing us to measure how the web has stretched and evolved over the last 11 billion years. Meanwhile, high above the distorting effects of our atmosphere, the European Space Agency's Euclid Spacecraft is conducting its own silent survey. Euclid sees the universe with two kinds of eyes. One instrument meticulously measures the shapes of billions of galaxies, detecting the tiny, telltale distortions caused by weak gravitational lensing from intervening dark matter. The other instrument maps the positions of these same galaxies, revealing the clustering pattern imprinted by the invisible cosmic skeleton. By combining these two powerful methods, Euclid is constructing a map of both the dark matter web and the luminous galaxies that decorate it, charting its geometry across 10 billion years of cosmic history. This is not science for the sake of a beautiful image. These colossal data sets are the raw material for answering the most profound questions in physics. The precise spacing between galaxies in the web acts as a cosmic ruler. By measuring how this ruler's apparent length has changed over cosmic time, we can trace the influence of dark energy and measure its strength with unprecedented accuracy. The way galaxies cluster together reveals the properties of the dark matter that guides them. Even the very nature of gravity itself is being tested, as these maps can reveal if Einstein's theory holds true across the vastest distances and deepest times. This golden age of mapping is a testament to human collaboration. Thousands of scientists and engineers from dozens of countries have united in this single, staggering endeavor to understand the architecture of reality. The maps they are producing are the most detailed charts of existence ever made, the direct inheritance of every stargazer and astronomer who ever looked up and wondered. We are no longer just observing the cosmic web. We are taking its measurements, weighing its components, and reading the history of its construction from the most detailed atlas of the universe ever created. Woven directly into the architecture of the cosmic web is a perfect measuring stick. This cosmic ruler is known as Baryon acoustic oscillations, a permanent echo from the universe's fiery beginning. To understand it, we must travel back to that early plasma, a searing soup where particles of light, or photons, were tightly bound to particles of ordinary matter, which scientists call baryons. In this dense fluid, gravity would try to pull matter inward, clumping it together, but the intense radiation pressure from the photons would fiercely push back, creating a powerful rebound. This push and pull generated colossal sound waves that raced outward through the primordial cosmos, traveling at over half the speed of light. These were not sounds anyone could hear, but vast, spherical ripples of compressed matter and energy expanding for hundreds of thousands of years. Then the universe cooled just enough for atoms to form. In an instant the fog cleared, the photons flew free, and the ripples in the matter were instantly frozen in place, like a wave caught mid-crash. This process left a distinct fingerprint on the cosmos, a subtle preference for galaxies to be separated by a specific distance, a scale of about 500 million light-years. You can picture this as if the early universe pressed a giant, spherical cookie cutter into its material, and the galaxies we see today preferentially formed along that imprinted ring. This frozen wave pattern is now permanently etched into the large-scale structure of the universe. When astronomers create their three-dimensional maps from projects like DESI, they do not just see the web's filaments, they can detect this faint, repeating signal within the data. By measuring the apparent size of this standard ruler at different distances, and thus at different eras in cosmic history, they can perform a remarkable feat. They can measure how much the fabric of space itself has stretched over billions of years. If the cosmic expansion had been constant, this ruler would look the same at every epoch. But it does not. The measurements show that the ruler appears progressively more stretched in the more recent, nearby universe compared to the ancient, distant one. This is the direct geometric signature of dark energy's accelerating push. It is as if we had a tape measure that changed its scale over time, and by tracking that change, we can weigh the invisible force that is causing it. This method provides one of the cleanest and most powerful probes of dark energy, entirely independent of supernova or other techniques. It uses the universe's own primordial echo, a fossilized sound wave, to take the dimensions of reality itself. With this tool, we are not just mapping where things are, we are measuring the fundamental forces that govern the entire cosmic stage. This grand cosmic architecture is much more than a beautiful sight. It is the ultimate laboratory for testing the laws of physics themselves. The immense scale of the web and the way its structures slowly evolve over billions of years provide a unique proving ground for Einstein's theory of general relativity. According to his vision, matter and energy tell spacetime how to curve, and that curved spacetime tells light and matter how to move. The cosmic web is the physical manifestation of this dance, a map of gravity's long-term influence. When we measure how galaxies cluster together, or how their light is bent by invisible dark matter through weak gravitational lensing, we are directly testing these predictions on the largest possible canvas. The frozen sound waves of Baryon acoustic oscillations serve as a perfect standard ruler for these experiments. So far, Einstein's theory has passed every cosmological test with remarkable precision. The way the universe behaves on the grandest scale aligns perfectly with the warping of spacetime his equations described. Yet, the search for any tiny crack in this foundation continues, as even the smallest deviation could open a window to new physics, to a deeper understanding that might one day unite gravity with the other fundamental forces. This cosmic laboratory also allows us to probe the secrets of the most elusive particles, ghostly neutrinos, which stream almost unimpeded through ordinary matter, have a subtle but measurable effect on the cosmic web. Because they travel at nearly the speed of light, they can effectively stream out of the universe's densest regions, carrying energy with them. This process gently smooths out the small-scale structure of the web, suppressing the formation of the very smallest clumps of matter. By meticulously mapping the cosmic web and counting the number of these tiny structures, cosmologists can effectively weigh the neutrino. This is a profound achievement, as these particles are notoriously difficult to study in terrestrial laboratories. The vast universe, with its patient, billion-year-long experiments, becomes our most powerful particle accelerator. This beautiful connection reveals a deep unity in nature, where the laws governing the largest structures in the cosmos are inextricably linked to the behavior of the smallest known particles. The great cosmic web is not just a skeleton of reality, but a bridge between the immense and the infinitesimal. These vast walls of galaxies are the continents of the observable cosmos. The Sloan Great Wall, one of the first of these behemoths to be discovered, is a staggering structure. It is not a solid barrier, of course, but a colossal sheet of interconnected galaxy clusters and filaments, a great curved plane that spans an almost unimaginable 1.4 billion light-years. To grasp that scale, a beam of light, the fastest thing in the universe, would take nearly twice the current age of our planet just to travel from one end of this wall to the other. Within this immense architecture dwells an entire civilization of galaxies, thousands upon thousands of them, all bound together by the invisible threads of gravity. Yet even this titan may not hold the record for long. Astronomers have identified an even more colossal candidate in the distant universe, the Hercules Corona Borealis Great Wall. Its proposed size is so immense that it challenges our ability to even define what a single structure is, sparking vigorous debate about its true coherence. The very existence of these walls pushes against a fundamental pillar of modern cosmology, the cosmological principle. This principle states that on the largest scales, the universe should look roughly the same everywhere, homogeneous and isotropic, with no single region standing out as special or unique. Finding a structure that stretches across such a significant fraction of the observable universe forces us to ask a profound question. What exactly is a sufficiently large scale? Is our entire observable universe still just a local neighborhood, too small a sample to see the true, smooth average? Or are we seeing the first hints that the cosmos possesses wrinkles of structure on scales we never thought possible? These great walls are the ultimate endpoints of gravitational collapse, the places where the cosmic web has drawn matter together into its most concentrated, sheet-like form. By studying their boundaries and measuring their vast emptiness, we are not just cataloging cosmic curiosities. We are stress-testing the very foundations of our understanding, probing the limits of where our standard models of the universe begin to fray. They stand as majestic, challenging monuments, reminding us that the map of reality is still being drawn, and its largest features are only just coming into view. These cosmic voids are the silent chambers of the universe. While the great walls are the continents of the cosmos, the voids are its abyssal plains, immense regions of profound emptiness that make up the overwhelming majority of the universe's volume. To call them empty, however, is a cosmic misdirection. A void is not a perfect vacuum. It is a realm of extreme scarcity, holding only a handful of isolated galaxies where a supercluster might contain millions, all suspended in a sea of incredibly tenuous, ultra-diffuse gas. This profound lack of density makes these voids the perfect laboratory for observing the universe's most elusive force. With so little matter present, the inward pull of gravity is exceptionally weak. This allows the repulsive push of dark energy to operate with minimal opposition, accelerating the expansion of space within these voids more dramatically than anywhere else. They are the places where the universe is stretching itself thin most effectively. The very shapes of these voids tell a story. They are not perfect spheres, but complex, amoeba-like volumes, their boundaries molded by the dense filaments that squeeze them from all sides. By meticulously measuring their morphology, their sizes, and their distributions, cosmologists can extract vital clues about the strength of dark energy and the overall geometry of the cosmos. The pattern of the emptiness is a direct imprint of the forces that sculpted it. Within these vast deserts, a special class of galaxy exists in near total isolation. Void galaxies are the cosmic hermits, evolving for billions of years without ever experiencing a close encounter with a neighboring galaxy. This solitary existence leaves a clear mark. Without the gravitational harassment and gas-stripping collisions that are common in crowded clusters, these galaxies often retain their primordial gas reserves, leading to slower, more steady rates of star formation. They are like time capsules, preserving a quieter, more isolated mode of galactic evolution that would otherwise be erased in the bustling metropolitan centers of the web. To truly understand the cosmic web, we must study both the threads and the holes in the fabric. The great walls and glittering clusters define where the universe is, but the voids define where it is not. This interplay is the key dynamic. As the universe expands, matter continuously drains from the voids, flowing outward toward the gravitational attractors of the filaments and nodes. The voids are actively being emptied, their material fueling the growth of the structures around them. By studying this cosmic drainage pattern, we witness the large-scale structure in a constant state of flux, a dynamic equilibrium between the relentless push of dark energy and the patient, gathering pull of gravity. The map of reality is not just a drawing of luminous points, but a careful tracing of the profound and defining emptiness between them. The grand architecture of our universe faces a slow and silent dissolution. The cosmic web, for all its majesty, is caught in a fundamental tug-of-war, a battle between the patient, gathering pull of dark matter's gravity and the relentless, repulsive push of dark energy. For billions of years, gravity has been the master builder, tirelessly drawing matter along the dark filaments to feed the growing galaxy clusters. But the balance of power is shifting. As the universe expands, matter becomes more diffuse, its gravitational grip weakens, and dark energy's influence grows stronger. This silent force is now beginning to dictate the long-term fate of all structure. Its first effect is to stifle future growth. No new superclusters or great walls will ever form. The era of cosmic construction is over. Then the process of unraveling begins. The acceleration of space itself will start to overwhelm the gravitational bonds that hold the web together. The delicate, thread-like filaments that bridge the vast distances between galaxy clusters will be the first to go. Stretched by the expanding void, these cosmic bridges will thin, snap, and finally drift apart, severing the connections between the universe's great metropolitan centers. The galaxy clusters themselves, those brilliant nodes of the web, will become gravitationally unbound from one another. Each cluster, along with its surrounding halo of dark matter, will become an isolated island universe, drifting alone in an ever-cooling, ever-darkening sea of nothingness. For any civilization remaining in our own local group far in the future, the sky would tell a haunting story. All other galaxies beyond our immediate gravitational family would have receded over a cosmological horizon, their light stretched beyond detectability and their signals forever lost. The universe would appear as a single, lonely island of stars in an infinite black ocean. This profound forecast reveals that the intricate, interconnected cosmic web we are mapping today is not a permanent feature of reality. It is a temporary, brilliant phase in the life of the cosmos, a fleeting moment of complex structure between a formless beginning and an isolated end. We are living in a special epoch, a golden age for cosmology where the universe is both transparent enough to see and structured enough to map. Our efforts to chart the great cosmic web are not just an exploration of space, but a race against the universe's own clock, capturing a singular, magnificent chapter in the story of existence before the final pages fade to black. These digital universes are born from pure mathematics and raw computational power. Inside a supercomputer, a simulation like Illustris TNG begins its life as a pristine virtual cube of space, seeded with the exact same minuscule density fluctuations we observe in the cosmic microwave background. Then, with the press of a button, the laws of physics are set in motion. The simulation tracks the gravitational dance of countless dark matter particles, models the complex hydrodynamics of swirling gas, and even attempts to capture the explosive feedback from supernova and the voracious appetites of supermassive black holes. This is not a simple animation. It is a rigorous calculation of cause and effect unfolding over billions of virtual years. The scale of this endeavor is almost beyond comprehension. A single run can consume millions of hours of processor time, tracking the interactions of trillions of individual particles as they coalesce into a vast, intricate cosmic web. When the simulation is complete, researchers can step inside. They can fly through this digital cosmos, panning across virtual voids that stretch for hundreds of millions of light years, and zooming in on individual galaxies forming at the intersections of dark matter filaments. The most profound moment comes when they place this virtual universe side by side with the painstaking maps from the Sloan Digital Sky Survey or the Dark Energy Survey. The resemblance is uncanny. The same great walls, the same filamentary bridges, the same statistical distribution of voids and clusters emerge from the code. This remarkable agreement is a triumph for our standard model of cosmology. It tells us that our understanding of the universe's ingredients, from dark energy and cold dark matter to the basic laws of gravity, is essentially correct. These simulations act as virtual laboratories, allowing us to perform experiments that would be impossible in the real cosmos. What happens to galaxy formation if we turn off the feedback from black holes? The simulation shows us that without this regulating force, galaxies would grow impossibly large and bright, completely unlike what we observe. How do different types of dark matter particles influence the smallest structures in the web? By altering the underlying rules, we can test these ideas and compare the results to our deepest observations. They are the essential bridge between theory and observation, a way of reading the story written in the light of distant galaxies and translating it into a fundamental understanding of the forces that shape them. Without these digital twins, the immense data flowing from our telescopes would be an impenetrable forest of numbers. The simulations give us the map to find our way through, revealing the underlying simplicity and order within the cosmic complexity. For years, our cosmic inventory did not add up. When cosmologists tallied all the normal matter they could find in the modern universe, the stars, galaxies, and visible gas clouds, the total was shockingly low. It was only about half of the amount predicted from the pristine conditions recorded in the cosmic microwave background. This glaring discrepancy became known as the missing Baryon problem, a major puzzle that suggested we were fundamentally misunderstanding where the building blocks of planets and people were hiding. The answer, it turned out, was woven into the fabric of the cosmic web itself. The missing matter had not vanished. It was simply hiding in plain sight, or more accurately, in the darkness between the galaxies. Scientists theorized it must exist as an incredibly diffuse, superheated gas known as the warm-hot intergalactic medium, or WIM. This gas is threaded throughout the vast filamentary network of the cosmic web, a ghostly atmosphere for the dark matter skeleton. Detecting it directly is incredibly difficult. It is too hot to glow in visible light and too thin to shine brightly even in X-rays, but its ghostly presence has been confirmed through clever, indirect means. When the intense light from a distant quasar travels across the universe, it passes through these filaments. The WIM acts like a cosmic filter, subtly absorbing specific wavelengths of that light and leaving a unique fingerprint of its composition in the quasar's spectrum. Another method involves looking for its faint shadow on the cosmic microwave background. As the CMB light passes through the hot electron gas in these filaments, those electrons give the photons a tiny boost of energy, a subtle distortion known as the Sunyaev-Zeldovich effect. These painstaking observations have confirmed the theory. The great majority of the universe's normal matter does not reside in galaxies, but in this vast, intergalactic web of hot gas. This discovery does more than just close a cosmic accounting error. It fundamentally changes how we see the cosmic web. It is not merely a gravitational structure of dark matter decorated with galaxies. It is a dynamic thermal ecosystem. This warm hot gas is the product of the universe's violent construction, shock heated to millions of degrees as it was funneled at high speed into the growing filaments and clusters. It is the primary reservoir of normal matter, the raw fuel that will continue to feed galaxy formation for eons to come. Finding these missing baryons is a profound validation of our entire cosmic story, confirming that from the first quantum ripples to the largest structures, we are truly beginning to understand the composition and evolution of everything that exists. Our own cosmic address places us on a quiet suburban street within an immense metropolis. The Milky Way, with its hundreds of billions of stars, is not a solitary island but a member of a small, gravitationally bound family known as the local group. This neighborhood includes our great spiral neighbor, the Andromeda Galaxy, the smaller Triangulum Galaxy, and dozens of smaller dwarf galaxies, all orbiting a common center of gravity. This entire local group is itself in motion, falling gently toward the heart of a much larger structure, the Virgo supercluster, a sprawling collection of hundreds of galaxy groups all centered on the massive Virgo cluster. For decades, this was the largest structure we thought we belonged to. Then, a new and more profound way of mapping revealed our true home. By studying the subtle streaming motions of thousands of nearby galaxies, astronomers identified an even grander structure, a continent of galaxies they named Laniakea, from the Hawaiian for immeasurable heaven. Laniakea is not defined by a dense central cluster, but by its gravitational watershed, the region of space where every galaxy within it flows inward toward the same great basin. At the heart of this immense basin lies a mysterious gravitational focal point known as the Great Attractor, a region so obscured by the dust of our own galaxy that its true nature remains one of the great puzzles of local cosmology. Our Milky Way resides far from this bustling core, on a quiet, outlying filament of this cosmic continent. This perspective is transformative. We are not at the center of this structure, nor are we in any special or privileged location. We inhabit an ordinary neighborhood in an ordinary supercluster, one of countless such structures in the observable universe. And yet, from this perfectly average perch, something extraordinary has happened. A species living on a tiny rock orbiting an average star has managed to not only conceive of this immense architecture, but to begin charting its boundaries and understanding its history. Our quest to map the cosmic web is the ultimate story of finding our place, not as the center of creation, but as its conscious cartographers, using the light of distant suns to trace the invisible skeleton of reality itself. This intricate architecture forces a question that transcends astronomy. What is the true nature of reality? The cosmic web is not a backdrop against which galaxies play their parts. It is the primary entity, a single, coherent organism. We are not isolated beings looking out at separate stars. We are temporary patterns within a continuous fabric, momentary expressions of a structure that was encoded at the very beginning of time. The fact that a microscopic quantum ripple could dictate the location of a galactic supercluster billions of years later shatters our classical sense of cause and effect. It suggests a universe where the smallest and largest scales are deeply, mysteriously linked in a way we are only beginning to fathom. Most of this reality is permanently hidden from our direct senses. We navigate a world of visible matter, of light and solid objects, yet the form of everything we see is sculpted by dark matter and is being stretched apart by dark energy, two forces we can only detect through their ghostly gravitational influence. The universe we experience is a mere shimmering surface on a deep, dark ocean. This hidden architecture is a physical manifestation of the underlying laws of physics, a mathematical skeleton that gives form and order to existence itself. Contemplating this vast, beautiful structure leads to one final, humbling thought. Is such intricate mathematical order a prerequisite for our own existence? Could a chaotic, formless universe ever give rise to conscious beings capable of looking up and wondering about its design? Our journey to map the cosmic web ultimately becomes a journey to find our own place, not just in space, but in a cosmos whose very laws seem to permit and perhaps even encourage the emergence of meaning. These stunning visualizations of the cosmic web have become the new face of the cosmos for our time. When you see a map from the Sloan Digital Sky Survey, with its delicate, lace-like structure of galaxies, or a supercomputer simulation like Illustris TNG, showing the dark matter skeleton in glowing purple tendrils, you are not looking at an artist's fantasy. You are seeing a data-driven portrait of reality itself, a map constructed from billions of precise measurements. This is a new cosmic iconography, replacing the old, comforting image of isolated island universes with a vision of a dynamic, flowing, and profoundly interconnected whole. The aesthetic is one of fractal complexity, where the same branching patterns appear from the smallest scales to the largest, suggesting a universe built on principles of elegant, repeating geometry. This new icon does more than just inform us. It changes how we feel about our place in the scheme of things. It embodies a deep, intuitive sense of wonder and a recognition of an underlying order that is both mathematical and beautiful. The image of the cosmic web has seeped into our culture, influencing everything from science fiction backdrops to philosophical discussions about connectivity. It serves as a powerful, universal symbol for the interconnectedness of all things, a concept that resonates just as strongly in ecology, sociology, and art as it does in cosmology. There is a profound truth here that the relentless, rigorous pursuit of scientific truth does not lead to a cold, sterile universe, but to one of breathtaking splendor and profound meaning. The ultimate reward for our species' curiosity is the discovery that reality, in its purest form, is more stunning and intricate than any story we could have invented. Our view of the cosmic web is permanently anchored to a single point in space and time. This unique perspective creates unavoidable distortions in our maps. One of the most telling is called the finger of God effect. When we look at a distant galaxy cluster, the intense gravity within it causes the individual galaxies to swarm at incredible speeds. Our redshift measurements, which we rely on to gauge distance, capture this motion. The result is that the entire cluster appears stretched and smeared along our direct line of sight, like a long, pointing finger, rather than showing its true spherical shape. We are seeing the cluster's internal chaos, not its actual geometry. This is just one example of how our position inside the system we are studying warps our perception. Another fundamental challenge is the sheer dimness of the most ancient structures. The light from the farthest filaments has traveled for so long that it arrives as a whisper, a photon here and a photon there. To make matters worse, vast clouds of intergalactic dust can act like a cosmic fog, absorbing and scattering this faint starlight before it ever reaches our telescopes. We are trying to map a continent by observing a few candles flickering in a distant haze. This leads to a humbling possibility. The grandest structures of the cosmic web, the true continents of reality, might be so immense that they extend beyond the boundaries of our deepest surveys. Our current maps, as vast as they are, might only chart a single room in an infinite castle. We are sketching the local geography without knowing if we are on an island or a mainland. Future observatories will push our vision further, but a fundamental horizon will always remain. There is a distance so great that the expansion of space itself will have stretched the light from galaxies there into utter undetectability. They will have crossed over a cosmological horizon, forever lost to our view. These limitations are not scientific failures. They are the natural conditions of being a conscious observer within the cosmos. They define the very nature of our quest. Our knowledge of the universe is, and will always be, a work in progress, a beautiful and ever-refined approximation of a reality whose full splendor we may never entirely see. This endless pursuit is the heart of discovery itself. Our next generation of cosmic cartography is already underway, its instruments poised to unveil the web with a clarity we have only dreamed of. The James Webb Space Telescope acts as a supreme time machine, its infrared gaze piercing the cosmic dust to witness the first strands of the web being woven. It sees the universe not as a finished tapestry, but as a loom in its earliest moments, capturing the faint glow of primordial galaxies as they ignite along the dark matter filaments. This is the cosmic skeleton in its infancy, a blueprint coming to life. Soon, the Nancy Grace Roman Space Telescope will join this grand campaign with a different, equally vital strategy. Where Webb looks deep, Roman will look wide, capturing panoramic views of the sky that will contain millions of galaxies. Its vast surveys are designed to measure the subtle warping of space by dark matter and the stretching of the cosmic ruler by dark energy with a precision that feels almost like reading the universe's finest print. Meanwhile, on the ground, an entirely different kind of sense is being activated. The Square Kilometer Array is not a single dish but a sprawling network of radio antennas, a colossal ear tuned to the faint 21-centimeter whisper of neutral hydrogen. This project will map the cosmic web not by its shining cities, but by its cold, dark rivers of raw fuel, tracing the distribution of the universe's most fundamental building block across unimaginable volumes of space. These observatories do not work in isolation. They are a symphony of perception. The deep infrared vision of Webb, the wide optical eyes of Roman, and the sensitive radio ears of the Escae will combine their data into a multi-wavelength, multi-messenger portrait of reality. This collaborative vision will allow us to watch the web assemble across cosmic time, from its first ghostly threads to its mature, glittering nodes. With this unprecedented data, we will perform experiments of cosmic scale. We will weigh the ghostly neutrino by the subtle way it smooths out the smallest structures. We will stress-test Einstein's theory of gravity across the vastest distances and deepest times, searching for any tiny crack that might point toward a deeper truth. The maps produced by this golden age of exploration will be more than scientific datasets. They will be a legacy, a detailed chart of the cosmos as understood at the dawn of the 21st century, a gift of knowledge for all future generations. This is not the end of our journey to understand the skeleton of reality. It is a magnificent new beginning, ensuring that our map of existence will continue to grow in both detail and wonder. This journey to map the great cosmic web fundamentally rewrites our cosmic address. We are no longer residents of an isolated star system, but conscious participants within a single, breathing organism that stretches across the entirety of observable space. Every filament, every void, every glittering node is part of a continuous whole, a structure born from quantum whispers and now steering toward an isolated future. The realization that an invisible skeleton of dark matter dictates the form of everything we see, while a mysterious dark energy controls its ultimate fate, is one of the most profound in human history. It moves us from being mere observers of the night sky to becoming active cartographers of existence, tracing the lines of a map that contains us within its design. This is not just a collection of facts, it is a new story for humanity to inhabit, a narrative where we are deeply connected to the largest scales of reality. The great cosmic web is the true architecture of our home, and our effort to understand it is one of the most meaningful adventures we can undertake. It is a story still being written, with every new telescope and every new simulation adding a line to the map. We invite you to share in the comments which part of this cosmic story resonates most deeply with you. Is it the ancient quantum seeds, the ghostly dark matter, or the silent pull of dark energy? Let us know your thoughts and subscribe for more journeys to the very edge of understanding.